Let's figure out if you did the solution math questions correctly, if you got the answers right, and if you still have a question, I may have the solution. So, for those of you that already attempted the questions, here are the answers point blank. For the first one, 0.0084 grams of calcium. For the second one, 0.013 parts per billion PCBs. And for the last one, 5.2 times 10 to the negative 4, so that's 3 zeros in front of the 5 with another decimal at that end. Parts per million for selenium. If you did not get one of those answers, please continue watching and I'm going to go through how I got those answers in case maybe one of those conversion steps tripped you up. We're going to go over that together. First and foremost, let's solve this first one here. If we're reading the question, we should note that we're looking at calcium hardness in water. Calcium hardness can be like magnesium, calcium, that's all the stuff you see crusted on the outside of your sink faucets. Anything like that can cause damage to a water heater, all that kind of stuff. And we found that the calcium hardness was 21 parts per million in the 2018 data for Portsmouth, which was a true value. And how many grams of calcium salts, that's just the actual calcium parts, if you will, would be present in a 400-gram glass of drinking water. So the first thing we need to think about is our parts per million equation, since we see that in the question right there. So we need to remember what our parts per million equation was. And that was grams of solute over grams of solution times 1 million, because it's parts per million in the case of this problem, is equal to parts per million. Now that we have that, we can just apply which values go in which places. So 21 parts per million is going to fit in the spot that has parts per million. We also have this number, 400 grams. Let's try and figure out where that's going to go. That's a glass of drinking water. We know that drinking water itself, is going to be more of a solution or a solvent and not so much a solute. So that 400 grams is going to be associated with the denominator down below. Therefore, the only value we have left is our grams of solute, which we can put an X there for. That's our placeholder from math. So that's like our X value, or a smiley face, if you remember from the last video. You can put a smiley face there. No one's going to judge you if it makes you feel better. Okay? Now we got to just plug and chug what we have. So that would be X over 400. And remember, we're treating this as a ratio, so we can put that in parentheses. Those things stay together in terms of PEMDAS, how we're going to go about algebraically solving this problem. And that's equal to 21 parts per million in terms of calcium. Always good to label still. Okay, so now the first thing we need to do is try and get X alone. We have this equal sign right here in the middle. That's kind of our wall, our barrier between both sides. And what I do to one side, I need to do to the other. And I'm trying to get X alone. So what I need to do first then is divide off the million. So I'm going to divide off the million on one side and also divide off a million on the other side. When I divide a million by a million, I get 1. So that essentially goes away. It doesn't do anything anymore. However, the 21 divided by a million on the other side results in a pretty small number. And that number is 2.1 times 10 to the negative 5. We still need to set that equal to our ratio from over here. So we can't forget that that guy still exists. Let's go back and set this up. So we've got our X over 400 is equal to 2.1 times 10 to the negative 5. Now all we have to do is get X alone. In order to get X isolated, we need to multiply in order to undo the division where the 400 is at the bottom here on both sides. So we're going to multiply this side by 400 over 1. That will effectively cancel out the 400 on this side because 400 divided by 400 is 1. It's pretty much the same thing we did up here to get rid of it. So now we have 400 gone on the left side, but we also, what we did to the left side, we need to do to the right side. So 2.1 times 10 to the negative 5 times 400 is going to give us 0.0084 grams of calcium. Oh, sorry, can't see that. There's grams of calcium behind my shoulder there. All right, so let's try the next one now. Okay, so for this one, it's a little bit more challenging to start off because we have to convert first. What we have here is a concentration in parts per billion. So we have to be thinking about our parts per million or parts per billion equation. In this case, it would be the grams of solute over grams of solution times a billion, due to that parts per billion now in the question, is equal to parts per billion. So we're looking at PCBs, which is a manufactured organic chemical additive, and there was a chemical spill. We're saying, hey, that ended up in the soil. So we have some chemicals in the soil in terms of, okay, we've got 0.06 milligrams of that stuff, that PCB stuff, dissolved in 4,600 kilograms of soil. Notice that our equation is in grams. Nowhere do we see milligrams or kilograms. So in order for this to work, we first need to get everything in terms of grams before we can plug it into our equation. So the first thing we're going to do is just kind of briefly review what milli and kilo actually means. So first and foremost, the unit milli is represented by m, and that is 10 to the negative 3. Or in other words, you've probably seen milli represented as 1 gram in this case in 1,000 milligrams. So you've seen milli as a unit of 1,000, right? But small scale. But a kilogram is the opposite. A kilogram is something big, kilo, big. So what we see then is that K is represented of 10 to the power of 3, or literally 1,000, right? In that case, we would say, okay, well, there is 1,000 grams in 1 kilogram. I'm going to explain both methods of using these as a conversion factor. There's two different ways you can think about it. Feel free to use whichever way is more comfortable for you. So the first thing we got to do is take the given value of 0.06 milligrams and turn that into grams. So our goal there is to make this a gram. Get rid of the m. So we can set this up as 0.060 milligrams, and I'm going to put the m, literally the m, in the bottom. Just as we saw from before, an m divided by an m is 1. It makes it go away, just like a number. So if I put the m in the bottom, that would just leave me with grams. Awesome, that's what I wanted. So the thing I need to remember is what goes on top. Milli is represented by 10 to the negative 3. Now all I would have to do is multiply these two numbers. Just like any math equation, when there's two numbers next to each other, you multiply. If there's number on top of another number, we divide. That's the reason why the milli can cancel, but the 10 to the negative 3 would multiply. If that's a method that you are uncomfortable with, another way of setting it up is 0.060 milligrams. And we know that there are 1,000 milligrams in 1 gram. So if we are looking to get rid of milligrams, milligram would still have to go on the bottom in order for those two to cancel, to divide out and equal 1. And gram would have to go on the top. That's my goal. Goal always goes on top. Goal goes on top. Just keep that in mind. So we've got 1 gram on top, 1,000 milligrams on bottom. Now you'll see if you do this either way, you'll get the same answer. So if you multiply 0.06 times 10 to the negative 3, you should be getting 6 times 10 to the negative 5 grams. If you do the same kind of idea with the bottom one, the 0.06 divided by 1,000, you will also get 6 times 10 to the negative 5 grams. It's just two different ways of converting, two different ways of thinking about it. So let's go ahead and convert the kilograms now as well. And now remember, we are doing this first because we can't plug in our values until we have everything in grams. So let's check out our kilograms now. We have 4,600 kilograms. And if I wanted to get rid of the K, remember that K is equivalent to 10 to the third power. So K goes in the bottom so that these can go away, and that's equivalent to 10 to the third power. So all I would do is 4,600 times 10 to the third power. Again, you could set this up instead as 1,000 grams being your goal. Goal goes on top, so grams goes on top. And that's equivalent to 1 kilogram in the bottom, in which case you'd get rid of the whole kilogram unit and be left over with the gram there. Either way, you get the same answer. In this case, if we multiply 4,600 by 1,000, we should get 4,600,000 grams. Excellent. So now we have converted our milligram and kilogram to grams. Now we can plug these things into our equation and solve for the ppb that the question is asking for. So let's go ahead and do that. My grams of solute are going to be my PCBs. That's what I have outlined in red here. So that's going to go on top. So 6 times 10 to the negative 5 is going to go on top. And then the thing that's going to go on the bottom is my solution or my solvent. In this case, it would be our soil because that's what the PCBs are dissolved in. So that would be 4,600,000 grams. We're going to multiply that ratio by 1 billion, and that'll give us our parts per billion, what we're looking for. Now remember, that was the overall goal of the entire question. We're trying to find the concentration that's in the soil. If we do this math out now, what we should see is that we get 0.013 parts per billion. Now again, remember that we need to divide this first, then multiply by the billion, and then we will get our parts per billion answer, which should be that guy right there. So hopefully you also got that. Let's try the next one. What is the concentration in parts per million of selenium if 1.3 milligrams is found in 2,500 kilograms of soil? So this is just like the last one in that we have to convert first our milligrams and our kilograms to grams. Remember, our original equation only has grams in it, so we need to fit our variables in terms of the equation's setup. So we need to make sure everything matches before we can plug and chug. Again, we are looking at parts per million like we were in the first question. So the equation we're using is grams of solute over grams of solution times 1 million this time, since the question is asking for parts per million, is equal to ppm. In this case, the question is asking for us to solve for ppm. So this is our big question mark, what we're solving for. Let's jump right into those conversions. Again, recall that milli is a unit of 10 to the negative 3. There are 1,000 milligrams in 1 gram. So we can use either ratio to convert our milligrams to grams. Let's set this up. So 1.3 milligrams is equivalent to m and 10 to the negative 3. That's the ratio to get rid of this m and be left with grams. Or, again, if you're uncomfortable with that, you can set it up as 1.3 milligrams. And we know that there are 1,000 milligrams. Again, the milligrams goes on the bottom because we are trying to get rid of it, and we are trying to be left with grams, like what's in our equation. We know that 1,000 milligrams is equivalent to 1 gram. So on this side, we can either multiply 1.3 by 10 to the negative 3. On this side, we would take 1.3 and divide it by the 1,000, since it's one number over another. Either way, you should be getting an answer of 0.0013 grams of selenium. Now we need to go back and convert our kilograms. We know that we have 2,500 kilograms of soil, and we know that kilo, that unit, is equivalent to 10 to the third power. We can also set this up just as before, if we wanted to, 2,500 kilograms, where we know that 1 kilogram is equivalent to 1,000 grams. On the first side, if we multiply the 2,500 by 10 to the third, or on the second side, if we multiply 2,500 by 1,000, either way we'll get the same answer of 2,500,000 grams, and that's of the soil now. Now we just have to plug and chug. Oops, sorry, my head's in the way again. So we need to plug and chug that back into our equation. My soil is going to be my grams of solution, and my selenium is going to be the thing that's dissolved in the solution, so that would be my solute. All right, so we've got 0.0013 grams of selenium divided by, just following our equation here, plug and chug, our soil amount, which is 2,500,000 grams of soil. And we're going to multiply that by 1 million, since we're solving for parts per million. And that should give us our ppm value. Again, remember, you want to do the things in the parentheses first, so divide those two values first, and then multiply by 1,000,000. Don't forget that step there. You'll be stuck with an answer that's incorrect. Make sure you remember to multiply by 1,000,000 after you divide. What you should end up with then is 5.2 times 10 to the negative 4 parts per million as your final answer. Alrighty, hopefully if you didn't get those right the first time around, you'll be able to answer them now with confidence. Give them a try again if you got them incorrect on your own, and see if you can get the answer right this time. Wishing you well, and I hope that you love science just a little ducking more.